And we're live. Good evening, Matt.
Morning, Hugo.
Good morning indeed. It's Friday morning here, but of course it's Science Thursday there. Science Friday here, but it's Science Thursday because most of us are in
In the past.
exactly. I live in the future and walk upside down over here. Um, I would love if everyone here, firstly, welcome everyone to today's very special Coiled birthday live stream. And what I'm just going to make sure, yep, we've got gallery view so people can see both of us currently. I'd love everyone joining to introduce yourself in the chat. Let us know where you're watching from, what your interest in Dask and or scalable Pi data is. That would be fantastic. And as you do so, if you enjoy these streams, hit subscribe and follow us on YouTube so you know when we're going live and what we're putting out there. So today we're talking about, and Matt will be speaking about accelerating the Dask scheduler. But I just wanted to let you know, you may be aware, this is a special live stream because it's our birthday month. So happy birthday to Coiled, and happy birthday Matt and Hugo and the entire Coiled family as well. And we've been doing these live streams for 9 months now. And the very first one Matt and I did together. So it's nice to bring the band back together, as they say. And
every other non-band member. That's really what's happening here, Hugo.
Exactly. And for our birthday as well, we're doing something special. We have, for the entire month, February 12 to March 12, we're opening up our product. So everyone, members, users, past and people signing up now, get 200 cores for free. So you get to burst to the cloud with your machine learning and data science workflows with 200 cores on us. So please do take advantage of that and spread the word as well. We've got a few happy birthdays. Guy Maskell, who's a regular, and Draw, both happy birthday. Christiana's joined in. Tim Harris, Pavitra, Kevin. So thank you all for joining. If you're joining just now, please do introduce yourself in the chat and ask as many questions as you'd like. Depending on the flow, we may get to a bunch of them at the end. But we'll see how things go. It'd be great to know also in the chat what your interest in accelerating the Dask scheduler is, because this is somewhat of an insider's story in a number of ways. But perhaps before jumping into it, Matt, you could tell us a bit about. I said to you, what would you like to talk to us? Talk to me, talk with me about, and talk to our audience about for our birthday. And you said you'd be really excited about this. So maybe you could give us a.
So I'll be honest, it's actually less about you, and it's also less about the audience. It's just kind of what I want to talk about. So
yeah, great.
So, right. Dask at certain scales starts to fall down performance-wise. There's been a big effort for a bunch of people over the last maybe 6 months in tuning it. And that's been really a fun technical engineering effort that I kind of, there's 50 things happening and no one really knows all of it. So I wanted to try to sort of assemble those things together and kind of deliver them. This is going to be like a slightly more technical and slightly maybe less organized talk than I normally give. It's my first time actually delivering this material. So like this seems like it would be a friendly group to try things out on. Then it'll get cleaned up in the future. But anyway, it's fun. It's one of the few technical topics I still actually have to be involved in Dask and Coiled. And so this is like the time in which I get to be an engineer and actually feel like I know what I'm doing, which running a company is not that.
Right. Well, I'll try to be as friendly an audience as possible and collaborator. I am interested for people who use Dask, how will this type of work impact them?
I'll get into that and talk about it. Maybe I should
Great.
Yeah.
Let's jump in.
Great. Okay. I'm going to share my screen. I've got a bunch of these little workspaces down here. You'll see 11, 12, 13, 14, 15, 16. So there's some slides we'll play around with, and then there's some like experiments we'll play with. I'm gonna start with slides and then jump into other stuff. But we're gonna sort of jump through a few different technical places. So I'm gonna start with this blog post, which we put out in July of last year called Faster Scheduling. And it talks broadly about the challenge of making the Dask scheduler faster. This is in the Dask blog. Hugo, if you put this into the YouTube chat, I think it would be a good place to start. And so again, this is sort of the start of this effort. And then since then, many people have worked on it, and we're going to give them attribution appropriately. but let's jump in. So we're looking at understanding scheduler performance. And we'll talk about why that's important, what that means, and then we'll talk about how we actually have worked on that. So it's gonna work. Yeah. Most people who've been working on this have been working either at NVIDIA, at Capital One, or at Coiled. I'm mostly presenting other people's work today. Again, I'll try to highlight folks and what they've done in particular. But I just want to put that out there. There's a few different companies that are involved here. Not just Coiled, it's not just me. It's actually not me at all, to a large extent. So I'm going to start with this broad theme. High performance isn't about doing one thing well. It's about doing nothing poorly. So if you have the fastest car in the world, it actually doesn't matter if your wheels don't work out well, or if your brakes don't work, or if you're too heavy to make a turn. High performance is a lot about doing a lot of things moderately well, rather than doing one thing particularly well. And we'll see examples of that. But that's sort of a fun theme that I always have in mind when I think about doing high performance computing. We're going to see a few things today. We're going to see a few motivating examples. We're then going to look at sort of the journey of a computation through Dask, all the way from your fingertips on a keyboard into the client, through optimizations, into the scheduler, into workers, and back. And that'll give us some understanding for some of those costs. We'll then jump into sort of high-level graphs very briefly and see how those address some of those costs. Then we're just going to jump into profiling. So a lot of doing high-performance computing is all about measurement. And there's a bunch of different ways to measure Python. We've actually tried, I think, all of them in this effort. And we're talking about sort of a few of the ones that we've used a bit. Then we'll sort of like end with the bag of tricks that we've seen, including just sort of standard Python micro-optimization. One of my favorites, Cython and Pure Python, which I think is something that came out of this work that was really cool. And then some other things. A bunch of other people worked on this or helped us out in different ways. And these are sort of some of their names in roughly the parts that they worked on. So again, we'll see these names again pop up later. Okay, so let's play with some motivating examples. I have too many tabs here. Yeah. So how does this problem manifest itself? So this problem manifests itself either if you have very short tasks or if you have a lot of workers. And so if you have very short tasks, we usually say try to make larger tasks. If you have a lot of workers, it does become an issue. So let's jump in and sort of see why that might be a problem. Let's make a function, f, which sleeps for some time, maybe a second, and then returns x plus 1. Now, if I were to run that locally over a list of data for x in range 10, I would expect this to take 10 seconds, which is going to be annoyingly slow. And this is a great time to use Dask, right, to avoid this sort of slowness of sequential computation. So we're going to sit here for 10 seconds here and just awkwardly feel that slowness. Great. So again, this is where you want to use Dask, right? This is a perfect case. And once we go through the perfect case, we'll see how the non-perfect case comes out. So I'm going to make a Dask client, and I'm going to, of course, bring up the local dashboard to see that as well. You're in the way, Hugo. I'm going to move you out of the way.
Happened before.
Yeah. So now, yeah. So if I want to I can run this same computation and map f over 10 numbers, and then gather results. So again, this is the ideal case, and this should take a second to run. So this is where Dask working really, really nicely. So this is the ideal case. The non-ideal case is if it's not f, but it's g, or rather than sleeping for 1 second, it sleeps for 100 microseconds. This function is way too fast for Dask to really make sense. And so if we play around with this much faster function, this is very, very fast. There's no real need to parallelize it. We could also, amp this up a bit. Why not do 1,000 instead of 10? We can still use Dask here, but it starts to make a lot less sense. In fact, Dask ends up making things slower. Right, so when we ran this sequentially, up here in cell 9, it took 160 milliseconds. We run this in parallel. It actually ends up taking longer, right? Just like the overhead of using Dask actually makes things slower than it would normally have been. And we can see that in the task stream here, because we look at our workers, they're doing a little bit of work, computing this G function, but there's actually a lot of space in between. And that's space where Dask is thinking, trying to figure out, the next thing that it should do. And Dask is too smart for this. It's spending too many cycles thinking about what to do instead of just doing it. And so this is a case where I think slow scheduling gets in the way, these really fast functions. Another case where this happens, you have, again, lots of workers. So another way we can sort of play with that or to simulate that with sort of more real data, you had a time series with many, many partitions. And you want to do something like sort that time series. There's actually a lot of tasks in there. There's sort of many thousands of tasks you have to run. And actually just handling all of those tasks ends up being slow. Again, we're spending most of our time in white space. So here we're doing this sort. Again, on this size of machine, it's fine. Dask is actually relatively well saturated. But as you scale out, these problems get a bit hairier. So this is broadly the problem we're trying to think about. How do we make the brains of Dask faster so that it can handle either more workers or very fast tasks? We try to motivate that in a different way with a movie of a barn raising. So this is going to show how I think about distributed computing. So I want to focus for a second. So we're not talking about how to make your entire computation faster, how to make your workers faster. For that, you want something like NumPy, Numba, Rapids to make your individual tasks faster. We care much here more about coordination or scheduling. And so to sort of motivate that, this is a video of an Amish barn raising. For people who don't know, the Amish are a sort of rural community in the United States that avoid modern technology. And so they are building a barn. You can see many people building this barn together using manual human techniques. And what I love about this is that this is a great metaphor for distributed computing. There's a really large task you need to do, building a barn, that no individual worker could accomplish on their own. But if you have many workers together, they can do that together. So the individual workers here, they're like your Dask workers. They're the ones who are running NumPy code, Pandas code, nailing in panes onto a roof. And to a certain extent, we're bottlenecked by how fast they can nail things. We're actually much more bottlenecked by the foreman at a job site like this, someone who's actually telling everybody what to do. And it's that coordination job, that job of, if a new person shows up, pointing to the right site, when he finishes that job, pointing to another job, that coordination effort actually ends up limiting teams of people to operate at speed. A modest foreman can easily handle 10 workers, but handle 100 workers or 1,000 workers, that requires someone who's going to be very, very sharp and very fast. Similarly in Dask, the workers are like the workers we see here. The scheduler is like the foreman at a job site. That's the person who's telling everybody what to do. And there's also the client, which is where we're typing in things. And that's kind of like the architect. They're actually building the plans for the things that we want to do. And to a certain extent, the users are the architect. You're the ones who are specifying the kind of barn you want built. So, and I want to sort of focus here for a second. We are mostly talking here about the cost of coordination and not so much the cost of execution. And that ends up limiting, again, the size of team that we can have. So, and I also just like showing this video. It's a fun video. Okay. So let's think about that journey of the plans from the architect over to the scheduler, the foreman, and then into all the workers as they actually start to do things. So that's going to be in 3 different phases, and we'll see the sort of 3 different roles that we have inside of Dask clusters: clients, schedulers, and workers. On the client side, there's us writing code. Here I've written a little bit of NumPy code, or a little Dask array code. That generates a high-level graph, where every node in that graph corresponds roughly to one operation in your code. So every sort of plus sign or transpose or sum is sort of represented in that high-level graph. So there are about roughly on the order of 10 nodes in that graph. Then we translate that high-level graph into a low-level graph, where now every node in that graph corresponds to one task for one worker. So as our data set size increases, this graph size increases. If we have a petabyte array, this graph gets huge, and that ends up being a real pain. Then we optimize that graph. You'll notice at the bottom, there's all these little chains of lots of little tasks that could all be done at once. We optimize it, they become just larger tasks at the bottom here. And so on the client side, this is like the architect. We're building the plans, we're fleshing them out, we're cleaning them up. And then we ship them off to the scheduler. We give them to the foreman and say, great, this is the thing I want you to build. Go and make this happen for me. The scheduler then takes those plans and it pushes it into its internal state machine, which is a complex mess of data structures. And then the internal state machine then talks to all the workers and it, on the fly, tells every worker exactly what task to do at any given time. So there are costs at every stage of this pipeline, right? We want to build a high-level graph that's pretty cheap. It's kind of small. It's not that complex. We want to lower that down to a low-level graph. That can be kind of expensive. We want to optimize that graph. That optimization step can be expensive. We then need to serialize that graph and push it over the network to the scheduler. That can also be expensive based on your network speed. We then need to go to the scheduler. We need to convert that graph into this sort of internal state machine representation. That can be expensive. And then there's this conversation between the scheduler and the workers. And this isn't expensive so much in like an event, but it's a constant drain on the scheduler. The scheduler is having lots of real-time conversations, one conversation with every worker. And as we add more workers, the scheduler now needs to keep up with more and more workers to sort of keep them up to date and to keep them fed and busy so they keep doing some work. Again, with 3 or 6 workers, you're totally fine. With thousands of workers, sometimes Dask starts to struggle a bit. And so the question really is, how do we make the scheduler, the foreman, able to make good decisions, but more quickly? And that comes into optimization. So we're going to start with sort of the first half of this pipeline on the client and then towards the scheduler. Then in the sort of latter part of the talk, we're going to talk more about the end, about the sort of state machine internal dynamics. So let's sort of just enumerate the steps we talked about. We construct a graph, we optimize it, we serialize it, we upload it to the scheduler. On the scheduler, we download it from the client. We sort of deserialize it. Then we go into the sort of conversational mode with the workers. Let's focus just on the client and scheduler part first. I'm actually going to do this live because I've been talking at a screen for a bit too long. So let's close this out. Actually, let's keep it open. Let's go over here. Yeah, so let's make this array. And then let's make, so Dask collections have a method in them called Dask graph, which is this sort of representation of all the different tasks. This is the thing that we're going to send to workers. And this graph for this particular computation has 25 elements. It's not that big. Let's maybe make it a bit bigger. Let's go to, let's see, how long should that be? Let's go bigger still. Yeah, so as I increase the size of my data set, the size of the task graph increases as well. Then as I do various operations to my array, the resulting collection, that graph will also get longer. Right, so now there's 470 different tasks there. Now we can see and look at how expensive it actually takes to build that graph. Right, so let's yeah. Right, this is part of the cost that we're going to think about. The next step, we'll want to optimize that graph. Right, so we might think about how long it takes to optimize things. Right, and that takes a few hundred milliseconds. We might then think about how to, sorry, I'm going to try to, do I have this in history? Let's see. No. I'm going to think about how to serialize that graph and how long that takes. And that takes, again, a second, a couple hundred milliseconds. This one's actually taking quite a bit longer than I expected. Oh, that's because I'm pickling the wrong thing.
Have you found yourself in something of a pickle, Matt?
Thank you, Hugo. Thank you.
All right.
Good to have you around. Yeah. So there's also things like serialization, right? And all of these take a bit of time. And what I sort of want to focus on here for a second is that they all take actually roughly the same amount of time. We actually could not have solved any particular one of these things and been totally fine. Also, sort of finally, all of the bytes that we collected in that serialization process was about 15 megabytes. We can just ship 15 megabytes across a wire. And if that's on your local laptop, that's pretty cheap. If you're shipping that over a network, so you're on a distributed cluster, that might be more expensive. And so overall, we're looking at sort of hundreds of milliseconds per stage in all of these different things. Added up together, that takes about like 1.3 seconds on this graph of 40,000 tasks. So if you've ever used Dask and you've ever hit compute or hit persist, and you found that Dask kind of lagged for a moment, and you didn't quite see the dashboard pop up quite as responsibly as you want it to, this is what's happening in the background. Dask is making graphs, it's optimizing graphs, it's serializing graphs, it's shipping them to the scheduler. And so that delay ends up being fine for a task graph of just 40,000 tasks, which is fine for almost everybody. We start hitting sort of larger workloads where you have millions of tasks, that could get into the minutes. And so this is sort of half of what we need to think about in optimizing the scheduler. And so this is, again, something to think about. We then need to sort of reverse a lot of those stages on the scheduler too. So these costs compound. And so the solution to this ends up being to use high-level graphs. This was sort of a large effort that happened later last year, led mostly by a gentleman named Mads at NVIDIA, but a bunch of other people sort of supported him in that work. And so going back to this image, what we do is that on the client, rather than making a high-level graph, low-level graph, optimized graph, we just decided to ship the high-level graph directly to the scheduler. And that is a far, far smaller thing to ship. But you might ask, well, wait a minute, like whatever happened to low-level graph expansion, whatever happened to optimization, like those pieces you can't just forget. And that's true. And I'm going to kind of skip over all of those things for a moment. Being able to skip those things requires a lot of care. And a lot of us are trying to very cleverly bake those systems back into Dask at the scheduler level. And that ends up being a complicated state. But this is actually released today if you set the right configuration values. And so today, if you have very large graphs, you might want to play around with this. The magic incantation is to provide the optimization fuse active flag and set that to false. So if you're using Dask data frame or Dask array today, that'll work. But you will be missing some of the low-level optimizations, which you may miss. But this is something that people can try out today, again, if they want to sort of see how fast we can ship things from the client directly to the scheduler and just have things start working immediately. For reference, in some of the major bottlenecks that some of the major benchmarks that NVIDIA does, this ends up being about a third of the computation cost. If you have very, very fast computations, as NVIDIA does, they've got GPUs to make the workers fast. Thinking back to our Amish barn raising example, imagine all of your Amish people were actually, like robots who could operate 1,000 times faster. Suddenly the scheduling problem, as GPUs sometimes are faster than CPUs, suddenly the foreman becomes a lot more bottlenecked, right? You have way, way faster communications. And so for NVIDIA, this is especially a challenge. Okay, so that's sort of client side. I'm now going to skip to thinking more about the conversation between the scheduler and the workers. And this part of things is going to be a bit different. We're going to talk more about sort of general Python performance and measuring and optimization. And so I think the first part of this talk is more about learning more how Dask works at sort of like the internals level. Hopefully some of that was interesting to you. The latter part of this is going to be more about how to profile Python in kind of extreme situations, and then some things you can do to optimize. So we've seen this, but so let's talk about profiling for a second. So profiling in Python or in any computing system is hard. So we say profiling, we mean trying to measure what's expensive in your code so that you can then focus on what matters. Measurement and metrics are critical to any system in making it run better. There are many different technologies here. We use everything. We mostly fell into these three tools, and we use all three of them. And they give us actually very different kinds of information that are all actually pretty useful. I'm going to start by actually going back to our example here with this sort of time series computation we ran. And Dask users may be familiar with the profile tab in the dashboard, which provides profiling information around all the different workers. So every Dask worker has a statistical profiler running on it, and then Dask merges all that information together on the scheduler and presents it in this nice bokeh dashboard. If you've ever seen a flame graph, this picture looks pretty familiar to you. If you've never seen a flame graph, this looks pretty foreign to you. But this is one technique we have for profiling in Dask, and it helps us understand both how the workers perform, and there's a secret plot that most people aren't aware of called profile server. There's actually not a button in the dashboard for this. This is actually profiling the Dask scheduler itself. So while Dask is profiling your code, it also spends a lot of time looking at itself. I actually realize now that I've actually turned off profiling, so this information is not going to be very rich. But there's a ton of information here telling you what's going on. This is one approach, and we use this a lot. It's really convenient for us because it's always running with Dask as a tool that you might want to use if you're using Dask to measure your own performance. There's a cProfile module. So we also run this nightly. So there's a great GitHub repository that's maintained by Ben Zaitlin, a longtime Dask maintainer. He currently leads the NVIDIA Rapids Dask team. And every night they run a benchmark that's very similar to the shuffle computation we ran just a moment ago, the set index computation. But they run it on a much bigger data set on a much beefier machine. And they post, every night there's a new issue, which just posts the results of that benchmark. Ben has really enjoyed this way of working. You can see a time series of performance over time, and also some raw data that gets printed out, and a profile plot. It also allows us to comment on what has happened over the last 24 hours. This way of working has been very useful for us just to keep track of what's going on and always have an artifact on which to base that conversation. So another way people often represent profiling information using modules like cProfile or PySpy or other techniques is with graphs like these. This is showing the aggregated time spent in every function with links towards the function that function calls. So for example, handle stream, this sort of teal color here, we're spending about 1.25 of our total amount of time spent. And within that, that function handle stream calls many different functions. It calls update graph HLG, it calls handle task finish, it calls cancel key, and others. And so you can sort of see the hierarchy of which functions call other functions. And so what ends up happening, honestly, is that John Kirkham is sort of another Dask maintainer, also at NVIDIA, looks at this plot every day, and he tries to find the hotspots, and he then goes and attacks that function. As you'll notice, most of these are blue. There's actually no sort of strong hotspots left. All the obvious things we've cleaned up. And I'll get into sort of sample a few things John has done, but this is looking very much at low-level Python code and tweaking, should we use a set? Should we use a list? Is there a certain method on a set we should use instead? So this is one way in which we capture information, and one way in which we then motivate or inform future development. The other sort of tool that I found very recently, was introduced to me very recently by a gentleman named Martin Brettles, is VizTracer. And this changed my world. I'm very excited to show people VizTracer. Martin Brettles has a great blog post actually on using VizTracer to track the guild. Let me bring that up and I'll sort of extol Martin's virtues for a moment while I do that. So Martin Brettles maintains the VX. I'm trying to pronounce it as someone from where he is from. VX is another Dask competitor. It is like a data frame library, but Martin has really focused on sort of optimizing performance here. It's very focused on pandas, but it's a cool library. Recommend people check it out. And Martin has been a great community activist in that he also works with a lot of other libraries. He helps optune pandas. He helps to promote other technologies. So he pointed me to VizTracer, and VizTracer gives a very different view on data, a very different view on performance to something like a profiler. So let me show people this. So I've run the Dask scheduler under VizTracer, and I sort of hit it with a bunch of workers and a similar computation to what we ran before with sorting a data frame. And what we're seeing here is every single function call that was run over the time span of about a second. And so I'm going to zoom in here a bit. And so what we're seeing on the top, again, we're seeing a hierarchy of function calls. So the add worker function, I'll click on that just for a second. This particular function call took 480,000 nanoseconds, so about half a millisecond. That function call called handle worker, which called handle stream, which called handle task something. These are kind of small here. And it just keeps going down. And so we're seeing every little function call that gets made inside of Python. Let's just zoom in further. And this just keeps going. It goes actually all the way down to individual Python operations. So you can see things here like the set method. The set class has a discard method, which took about a microsecond. And that called the hash method of some object. Looks like this is a hash method of the task state object. And so this information is far less aggregated. Right? So if we look again at some of information like this profiler, or this sort of tree of summarized function calls, this gives you a broad picture about everything that happened over the entire computation. With something like VizTracer, you actually get every single function call on a nanosecond by nanosecond basis. And so what we do actually is we look at this, and there's just hundreds of little stories that we can tell by looking at this code. And I won't bore you with all of those stories, but it's quite fascinating as a maintainer to look at data this rich. So anyway, this is sort of one thing to think about. And there's an issue which is very fun if people want to look at it, called, I think it's at the very bottom here at the moment, profiling scheduled performance. And many people are in this issue just looking at these VizTracer results and just going through different scenarios and what's correct or incorrect, or what should be tuned next. So again, this is active as of 5 hours ago. If people want to go look at this, this is issue 4443 on the Dask distributed issue tracker. Super fun if you're really into high performance profiling. There's a lot of very deep conversation in there. Okay. With profiling technologies. Right, so that was me going on about measurement for a while. Quick question, Hugo, any questions in the chat? I'm diving deep into technical things and I have no idea if I'm totally past everybody. I suspect that most people find this.
We're pretty good.
Okay.
Yeah. Great. But of course, I once again encourage people with any questions to ask in the chat.
Okay. Let's now jump into a few examples of optimization. I actually want to focus on one in particular, which is Cython and PurePython. This is something that I think John Kirkham proposed recently. I think this has actually a lot of potential in other Python projects. So I wanted to focus on this as one of honestly like 50 or 100 different optimizations we've done. But it's pretty fun. So, right. People may know of Cython as the thing that pandas is written in, right? So a lot of performant Python libraries aren't written in Python because Python is too slow. They're written in a different language called Cython. And so this I took from a blog post that I had written where I ripped off some code that Jake had written. So I'm crediting him there. This is showing Python and Numba on the left with the same code written with Cython on the right. And Cython adds a lot of types to Python in order to make it faster. So Cython takes Python-like code, compiles it down to C, and then produces a Python module you can import from normal Python. And so it's a way to write C-like code or to C-speed code, but from a Python familiar syntax. Cython is great. It has powered pandas, scikit-learn, PyTorch, not NumPy, lots of other Python libraries. It's critical to the ecosystem. It's also kind of a pain to use. So ways in which it's not great. It's not actually Python. You can't just type it into a terminal and have it run. It's a little bit harder to debug. It's hard, you can't sort of step through code. There's also this compilation step, which ends up slowing down development. As Dask maintainers, we didn't want to introduce Cython into our development flow. We actually find that working in pure Python really helps us to quickly understand and diagnose tricky issues. By far, Dask is better by being smart than better by being fast. So there's this sort of trade-off with Cython. Now, what's actually very neat is that as of very recently, you can actually write Cython code in pure Python using Python type annotations. So on the left, I've got some Cython code, which uses these sort of tricky things like cdef. We see this weird type annotation. It's also a .pyx file, not a pure Python file. What we can do now actually is that oddly, you can actually just write these same things, but with normal sort of Python 3 type annotations. So we're still typing things. We've sort of imported the double object from the Cython library, for example, but this is still a valid Python code. So we can still run it from a normal Python interpreter, or we can choose to Cythonize it, and we can do either or. And that split ends up making things really flexible. Most developers get to stay in Python most of the time, but when we go to package things to release them out to the community, we can choose to accelerate into Cython, and that gives us sort of the best of both worlds. Let's just look at a few PRs, sort of see how that looks. So here is an example. Most of this work was done by John Kirkham. This is an example of him Cythonizing one particular method inside the Dask scheduler. And so what we notice is that most of the logic is the same, but we add a bunch of type annotations at the top. So you'll see things like double in here. And there's some other sort of small changes. Right. A lot of our code has now been typed more aggressively, and we've had to sort of clean things up a little bit. So generally speaking, the Dask scheduler code got a lot more static, but not in a way that most people will notice or really care about. And so again, if you are using Dask today, this isn't going to be running for you. We don't publish this by default. But if you want to, you can run Cython over the Dask code base, and it does get faster. And it's, again, very fun to start seeing where we can identify hotspots and where we can make things faster.
So Matt, we have a great question from Carol Willing. How long has this been possible?
I have no idea. It's great to hear from you, Carol, by the way. Carol's a core Jupyter maintainer, and also I think used to be a PSF board member. Maybe she stepped down recently, I'm not sure. Yeah, it's a great question. I don't know. One would have to ask Stefan Banel, who I think does a lot of the Cython maintenance. I would say probably over the last year is my guess, but maybe someone else in the chat knows. Anyway, it's exciting. This sort of opens the door for us to write Cython, for people who know how to write Cython code, to write Cython code without bothering everybody else. And that ends up being sort of like a really good community split. John can like maintain performance while the rest of us think about like nitty-gritty scheduling details. And that sort of allows the two different skill sets to coexist in this same code base without interfering with each other.
So Matt, we have a couple more questions. They're coming hard and fast from some heavy hitters in the crowd. Deepak Cherian wants to know how much faster? 2x, 3x?
Yeah, that's a great question. I'm not just name dropping now. So Deepak is an X-Array maintainer.
Who has also appeared on Science Thursday as well to discuss his work at NCAR.
That's a great question, Deepak. Let's go and look at VizTracer, my favorite tool. So let's go and take a look at, for example, so a lot of what we look at is this transition code. Transition is like the state machine transition logic inside of Dask. So let's jump into one of these calls. So this transition call happened whenever it looks like a task was finished. So one of your, in your case, a NumPy call was finished on some worker. The worker reported to the scheduler, said, hey, I did this thing. What's next, boss? Turns out that task had a lot of dependencies. And each of these little pink boxes corresponds to one dependence on that task. If you recall, this is coming from a shuffle computation. So there's a lot of dependencies on each task. This is kind of like a rechunking operation in X-Array. If we look at just one of those transitions, so transitioning, looks like we are transitioning one of these tasks from memory to released. Let's dive in even further. What we're going to see here, whoops, too far. I'm using a ThinkPad and the little like nub is a little bit sensitive. Yeah, so you can see here calls to things like set.remove, and we're not going to make that faster, right? That's a call to like a hardcore C function. And then there's this other call to a Python function, get n bytes. And there's this space in between, right? And that space in between is space in between Python function calls. That might be iterating through a for loop. That might be waiting on C eval in the C Python interpreter. But that space is kind of indicative of the potential that we have to speed things up, right? And so I think this one actually isn't run under Cython. I can pull up one that was in a moment. But what we would expect to see under Cython is that these white spaces start to go away. And it's just those sort of things packed more closely together. So in principle, we should expect from Cython 2 to 5x, maybe, but maybe a lot more. The Cythonization is only part of what we're doing too. There are a lot of other stories that are happening in here. Let's see if I can find one. A big bane to our existence right now is extract serialize. Yeah, there we go. Sometimes Dask sends around messages that have like big NumPy arrays in them. And we need to go into those messages and rip them out to send them on a different channel. This is a performance optimization that Dask does. It turns out that actually like doing this reaching into messages and pulling it out takes up a huge amount of time, like 30% of our time. So this is a big opportunity for speed boosts.
And Matt, we've just got a couple of other questions. Jonathan Moore is interested in how Cython compares with Number for this kind of acceleration. And another question from a bit earlier, Marius. Hey, Marius Van Neerkerk. I hope I pronounced your name correctly. Asks that with the code you're writing, does this work with fancier annotations like dict, open square bracket, int, double, close square bracket?
Yeah, both great questions. Yeah, so Numba was not designed to do this kind of stuff. I would not be surprised if Numba was a bit faster, but it's really not designed around sets and dictionaries and things. That has changed over the last year, especially there's thought more about things like sparse arrays. But generally speaking, I would not expect a ton from Numba. I would love feedback from Numba developers who should be focusing this way, let me know. But I've also like talked to Sue and Stan a lot about Accelerator and Scheduler, and they've generally speaking tried to push me away. In terms of the dict int thing, I think there's actually an issue about that. I think the answer that I got from Stefan was no, that is not. Cython does not currently handle complex types. However, you can type things within sort of C Cython mix, much in the same way that you would in C, right? And so, for example, here's a good example. Processing is a dictionary of task state objects, but we can't annotate WS to processing to get that full annotation. We can separately just say, look, the pronoun TS is a task state object, and we can tell Cython that ahead of time. So Cython won't get, I think, fancy algebraic types. It doesn't do that yet, is my understanding. At least it didn't 6 months ago. But we can still tell Cython that information out of band.
So just a time check, Matt, we've got 10 to 15 minutes left. Yeah. We're good going over as well, but.
No, we're at a good time. This is the exciting part, I think. Awesome. But I mean, to both Jonathan Moore's question and to Marius's question, it's we've actually investigated all of this very, very deeply. We've had deep conversations with every single possible Python accelerant project. In fact, I think there's just an issue. Yeah, there's an issue. Accelerate the schedule with Cython, PyPy, C. Numba gets thrown in there too. This is from a few years ago, and this is also, I think, a good issue for people to look into if you're interested about the different options that are available here and how they've performed or not performed. Dask presents actually a very interesting target for these technologies because it's relatively high visibility right now, and it's a very interesting code base. It's atypical, and so like we've spent days with the PyPy developers, for example, just trying to see how far we can get. We've spent I've sat down with the Cython developer trying to see what we can do, and it's sort of a fun project to play with. What's really exciting is that now all of this is kind of coming to a head, and we have all of these engineers, again, from Coiled, from NVIDIA, from Capital One, pushing on this effort jointly. There's now a lot of engineering work pushing on this, now that we kind of have a plan in place. Okay, so that's all I want to talk about. There are a few other pull requests we can go into if people want to, but we should probably close it out here. I'll end maybe just with this, again, the statement again that high performance computing isn't about doing one thing well, it's about doing nothing poorly. And so I have skipped over 50 different projects that we've done in accelerating this stuff. And each project gives us 1%, 2%, 3% differences. But together they're starting to add up to some real changes. It's also interesting because there's really no way to make this fast with just one person. We actually there's no individual, knowing most people who could possibly do this work, there's no individual who could possibly do this work. It actually requires a sort of interesting team of people all providing a lot of input and a lot of effort. So it's been great to see.
So thank you, Matt, and thank you for everyone working on this stuff. It looks like we've got someone else joining the call. Hey.
Yeah, I was watching the stream and checking out the YouTube chat. Thanks for the great presentation, Matt. Here you go. Something I was wondering about, something you didn't touch on was some of the pain points that this group experienced when going from shipping the graph from the client to the scheduler, a high level version of that. I imagine is a heavy lift. So what were some of the pain points that the group ran into?
Yeah, that's great. That's a good anti-leading question. I think James knows a lot about that pain in particular. Yeah, so we actually stopped releasing in October of last year. There were about 2 months where Dask just didn't issue a release so that we could do this big transformation of moving high-level graphs rather than low-level graphs. And that, there's a lot of finesse to getting that right, and we didn't get it right, which is not surprising. And as a result, the release that was 2020-12 was actually broken in a few ways that took us about a month to find and fix. And so there were this was maybe a snafu of the Dask community. There was a kind of a broken-ish release for a while. We think that's over now. There's still lots of things to fix, but all the changes are now much smaller and much better understood. So that's definitely a thing that happened that we hope not to repeat. Our apologies. Yeah, that's probably the biggest thing. There have been other challenges, right? So profiling this stuff is a mess. The Dask code base is hard because it's really low-level Python stuff. We're optimizing way down to this set.add calls. It's not big things like NumPy calls. It's also highly concurrent, so a lot of Dask code calls itself in an event loop, which ends up being kind of tricky. And there's a lot of networking going on. And so all of those things combined together actually make it really, really hard to measure. And so I think every person on this project has their own favorite measurement technology, all of which gives us different results. And so it's interesting sort of trying to optimize a thing you can't quite see. James, any other challenges to bring up?
So like those are great points. A couple of the points I was kind of thinking about were like maybe more technical points, like the scheduler. We don't want to pickle on the scheduler, for instance. So like actually shipping the high-level graph representation to the scheduler, we have to like change our high-level graph representations and like add new functionality to that to be able to just, you know, mechanically ship them over to the scheduler. That's like a big pain point. So we're rewriting a lot of the high-level graph structure there, which is exciting. Now I can, if I turn Fusion off, I can compute a large, like a huge Dask array, and it just, almost instantaneously is shipped to the scheduler. I get my Python session back. It's not just sitting there waiting for, 5 minutes or something like that, processing the graph, which is great. But it did require a lot of re-architecting under the hood.
Yeah, and continues to require that. Yeah, so this is what James is bringing up is like, there are these steps that have been in Dask since the beginning, these low-level graphs and this optimization step. And we're kind of getting rid of that. There's like a bunch of code that's been in Dask since 2014 or whenever Dask was first created. And like that's going away. And we now need to re-implement that in a very different way, in a much more constrained environment. So we're shifting a lot of the burden from the client over to the scheduler. And that's good because it's a more constrained environment. We can be faster there. We like have the opportunity to use Cython there, for example, as well. But it also requires us to like not actually look at Python code. The scheduler, for reasons of security, can never undeserialize anything. The scheduler can never look at a user-provided object. The scheduler doesn't have access to all the same things that the client does. And so we've had to sort of figure out how to do all the optimizations that the users are used to in this different, far more constrained environment. And that is like, there's individual talks we can give on each of those different topics. And we will, hopefully. There's a good call out. So we're planning a Dask user conference in, I think, May. I think sort of May 19th is sort of the hypothetical date. There should be a launched website, I think probably early next week. And we hope to actually have a track, which is an expanded version of this talk, where everyone who's done this work is talking about the various pieces that they've done. And there's, again, a bunch of very interesting engineering that's gone into this. And there's a lot of good potential here.
And if you're interested in the summit, we'll announce it on Twitter, and Dask Dev on Twitter will as well. So if you follow either of those accounts, you'll find out.
Presumably, if you found this live stream, you will also find the Dask user conference.
Absolutely. We have a couple of final questions in the chat. Guy is asking, is there a top recommend? So this is a bit more general. Is there currently a top recommendation for Dask and Python versions? For example, no, you want to use Python 3.6 or don't use 3.8.2, whatever it is.
Go for it, James.
You don't want to use Python 3.9 today. Hopefully, not literally tomorrow, but hopefully tomorrow, like in the next week or so, that answer will change. But today we support 3.6 through 3.8. So anything in there should be totally fine.
Yeah. There were some weird multiprocessing things that happened in Python 3.9 that I think Guido Imperiale is now like fixing to our great pleasure. And then
to Matt's earlier point, like latest Dask release, that there was sort of this discontinuity in support for like a brief moment. The latest release should be totally fine. We are past that pain point, hopefully.
The flood is over.
Yeah.
And Keith Pascoe has a question around Coiled, it seems. Will any scheduler visualization debugging tools, as discussed or otherwise, be integrated into the dashboards in Coiled?
Yeah, so so you can currently look at the existing Dask dashboard in Coiled. Coiled just brought two things through. We are also thinking about sort of other broader terms like multi-run dashboards in Coiled. It's probably going to happen sometime later this year. The sort of advanced profiling stuff I showed today, things like VizTracer is probably not appropriate to put inside of Dask. Like 1 second of a recorded computation results in like 100 megabyte HTML file. So like that information is just way too dense to present live in any kind of reasonable way. But it does give us good ideas for the kind of computations or the kind of visualizations we could provide. So yeah, I think Dask has gotten a lot of mileage out of its dashboard. People love it. And there's a lot of more value we can do, both inside of Dask and inside of Coiled, which again has more sort of like longitudinal understanding of what's been happening.
Great, I just want to say I was very impressed that you were able to both show the VizTracer stuff and share your screen while streaming. That was very impressive.
People who use that tool will report that it does take like seconds to respond many times.
So it's time to wrap up. Matt, we've gone to GatherTown previously. I'm wondering if you're interested in having a small hangout in GatherTown.
Sure. Yeah.
Yeah, let's do that. There are a couple of hanging questions, but if we didn't answer one of your questions, please join us in GatherTown, and we'll be chilling there. I'm going to put a link in the chat now. I'll ask that James if you wouldn't just mind making sure that before we hang up that link is correct. That would be fantastic. And everyone who joined, thank you so much for joining us once again, particularly for our birthday. If you are interested in checking out our product, go to cloud.coiled.io, and we're looking forward to seeing you in more live streams and in more events and at Coiled.
It's also worth noting we are hiring. So I wrote a blog post about a month ago about sort of a 1-year summary. If you like doing this work, like we're doing interesting work like this and other more boring work, less boring work, please submit an application. We're at jobs.lever.co/coiled. If you put a link to in the YouTube channel, also good thing to do.
Fantastic, and I will do that right now. And it looks like a lot of people have just joined GatherTown, so the link worked. Mm-hmm. Cool. Thank you once again, everyone, and we'll see you in a few minutes in GatherTown. And thank you, Matt and James.